Okay, here we go. On Friday, we did some curve sketching, and we didn't do anything new. I mean, that was stuff you've seen before. Now we're going to do with a rational function, and we're going to do with a couple pieces. We might even get to a trigonometric function, which will be fun as well. But here's the following guidelines to sketch this curve. 3x over x plus 2. Now, the first thing I want you to do is I want you to identify. You should be able to look at this and understand it's a rational function because it's expressed as a fraction. And you should be able to look at it really quickly and identify what the vertical asymptote is. Where is this function undefined? -2. So you have a vertical asymptote at x equals -2. So that's a really important part of the graph because that's going to be a critical point. Well, it's not part of the domain, so I guess technically it's not a critical point. But that's where things can change, things can happen. So horizontal asymptote is going to be kind of the end behavior of the function. So I'm going to write EB. And the end behavior is as x goes to infinity. Now, I'm not going to make you show this every time. On your tests, you'll have to show them algebraically for the problems we did last week. But look at this problem right here, 3x over x plus 2. As x goes to infinity, do you know what the limit is going to be? 3. So what Larry does is he looks at the largest degree in the numerator and the largest degree in the denominator, which are really these two. You just divide them and you get 3. That's the quick way of doing it, okay? So you should be able to look at that and say, yes, y equals 3 is my end behavior. X and y intercepts. The y-intercept happens when what is equal to 0? Let's plug in 0 for x. 3 times 0 divided by 2. So the y-intercept is 0. Good. The x-intercept happens when the function is equal to, so 3x over x plus 2 is equal to 0 over 1. Watch what happens when you cross multiply. When you cross multiply, what happens to the denominator? It goes away. You're left with 3x equals 0. So basically, when you set a function equal to 0, you just have to look where the numerator is equal to 0. Where is the numerator equal to 0? So we've got our x and y intercepts. We've got our end behavior. We have our asymptotes. This is a lot of very good information. But right now, in order to answer questions about increasing, decreasing, and concavity, max, mins, inflections, what do I have to do? Derivative. So let's find the first derivative. In order to find the first derivative, what rule will I have to use? I will have to use the quotient rule. Quotient rule says take the derivative of the top, which is 3, times the bottom, minus the top, which is 3x, times the derivative of the bottom, which is 1. Divided by x plus 2, that quantity squared. How does that simplify? What does the numerator simplify to? 6 over x plus 2 quantity squared. So, where is the derivative undefined? -2. Are you surprised? No, we have a vertical asymptote there, so therefore the derivative cannot be identified there either. Now, I want you to think about this derivative very carefully, though, okay? I'm going to put it right up here. Everybody look at the first derivative. The numerator, true or false? The numerator is always positive. True. True or false? The denominator is always positive. True. Why? When you square it, it's going to be positive. So, the derivative is always positive. Therefore, the function is always increasing. Always increasing. Okay? The derivative is always above the x-axis. Yes, because it is positive. However, the function itself is always increasing. So there's no decreasing. Your increasing will be from negative infinity to negative 2, and from negative 2 to positive infinity. I have negative 2 because you have the denominator undefined at negative 2. That's our critical point. So, look at the derivative. Is the top ever equal to 0? Is 6 ever equal to 0? No. So therefore, the derivative is never equal to 0. So therefore, I do not have any max or mins. If I want to talk about concavity and inflection points, I have to look at the second derivative. So let's find the second derivative. F double prime of x is going to be equal to, what's the derivative of 6? 0 times the bottom, which is 0, minus 6 times the derivative of the bottom. How do I find the derivative of the bottom? Chain rule, very good. So u squared, x plus 2, take the derivative, I get 2u, and I get 1. So you get 2x plus 4 divided by x plus 2 to the 4th. Watch the tricky algebra in this situation. You've seen some of it before. Watch it again. F double prime of x is equal to, I'm going to take a 2 out of here as well. So I will have a negative 12 times x plus 2 over x plus 2 to the 4th. You okay with that? Why did I take out that extra 2 to make negative 12? Because then one of the x plus 2's will cancel. My second derivative is ultimately negative 12 over x plus 2 to the 3rd. So that is the simplified derivative. Second derivative, excuse me. I'm going to put that on my number line because that's like where I like to keep my stuff. Negative 12 over x plus 2 to the 3rd power. True or false? The top is always negative. True. True or false? The bottom is always negative. The bottom is not always false. The bottom is not always negative. The bottom is not always positive. It changes. So therefore, we must test. We want to know, we've already said that the derivative is always positive, so it's always increasing. But we have not said anything about the second derivative. We must therefore test points. What point would you like to plug in? Let's plug in negative 3. Negative 3 plus 2 is to the 3rd. Negative 12 divided by negative 1. So therefore it is positive, so it is concave up. So we are concave up from negative infinity to negative 2. What number to the right of negative 2 would you like to plug in? 0 is a great number. 0 plus 2 to the 3rd. Negative 12 over 8. Negative. So therefore I am concave down. So negative 2 to infinity is my concavity, where I'm concave down. There was a lot of debate about this last year. A lot of people really wanted to make it a point of inflection. And but you're absolutely right that it does. I mean, if you're looking for the spot where it changes concavity, negative 2 would be the spot. The only thing is, technically, in order to identify that, it has to be part of the domain. So we don't list it as an inflection point because we can't plot it. But without a doubt, it would be correct to say negative 2 would be a time where you would change inflection. You know what I mean? So we'll leave it at that. We do have no inflection because the top is never equal to 0, and that's really the answer. In order to have an inflection point, the top has to be equal to 0 at some point. So let's see what we have here. We know a little bit about this. We have our vertical asymptote. I'm going to draw my horizontal asymptote as well. And so you can see I have these two asymptotes. So the graph must follow the asymptotes. We know we have x and y intercepts that happen at 0 and 0. So you tell me, let's look at the second part of the graph. Will the second part of the graph be in the top portion or the bottom portion? Bottom, because I know it passes through 0, 0. So therefore, it must follow this asymptote, pass through 0, 0, and then follow that asymptote. Look at it. We said that the function is always increasing or always decreasing. Is it increasing? Yeah. Is it concave up or concave down? Concave down. So you can see that all those pieces do tie together. If you were to draw this in the upper portion, it would be decreasing and concave up. So it has to match with what we've said. Look at this part right here. We don't have a point that it passes through, so we have to be smart about it. We know that it's increasing, and we know that it's concave up. If I draw it in the bottom, is that increasing and concave up? No. If I draw it in the top portion, is that increasing and concave up? Yes. So therefore, I draw just like that. Since the derivative is always positive, the graph of the derivative would always be above the x-axis. But this is the graph of the original function. Okay. All right. This is my favorite part. Let's check to see what it looks like. 3x divided by x plus 2. Yep, thank you. X plus 2. And this looks about what my window is like. Oh, I don't really get that. What's going on here? Okay. So there we go. Now we see that portion. As you notice, my TI-83. This is unlike your TI-84. Your TI-84 will not show the asymptotes. My TI-83, it shows the vertical one. It's not going to show the horizontal one. Okay. So if you'd like to, you could insert it. Y equals 3, and then there you go. So wait. All right, let's try another one. Yeah. This one's a little trickier. You tell me. Let's start with the asymptotes. Vertical asymptotes. Where's this function undefined? 1 and -1. Yep. Folks, Okay, we got -1, we got +1 for our vertical asymptotes. Can anybody identify what the horizontal asymptote is? Y equals what? Very good. 2x squared divided by x squared gives me 2. So if you were to take the limit as x goes to infinity or negative infinity, you would in fact get 2. So y equals 2 is your horizontal asymptote. Now, I'm going to draw this horizontal asymptote right now, and I want you to understand something. The horizontal asymptote tells us our end behavior. So end behavior would be out there, and end behavior would be out there. Is end behavior in the middle? No. So I'm not going to draw it in the middle. The graph can exist in that middle portion. It could cross that line conceivably. Okay? So therefore, I kind of have these parameters set up for what the graph looks like. Now we just have to verify where it is. And again, as you ask that question of, well, why can't we just punch in our calculator? Remember what Isaac Newton was doing 400 years ago. And instead of plugging in, 40, 50 points for x and y and coming up with, dots and plotting them, he was able to go through this method pretty quickly. Okay? So, I sure will. Horizontal asymptote, one more time, if you have the limit as x goes to infinity of 2x squared over x squared minus 1, what do you factor out of the top? X squared out of the top. What do you factor out of the bottom? Times 1 minus 1 over x squared. And you can see that the x squareds will cancel, and you'll be left with 2 over 1, which is 2. So it always just ends up being that you can basically circle the largest powers in both the numerator and the denominator and reconcile what the derivative is, or what the limit would be from that. Okay? Does that help? Okay, let's do x and y intercepts. X-intercept happens when the function is equal to 0, or the numerator is equal to 0. Where is 2x squared equal to 0? 0. The y-intercept happens when x is equal to 0. Plug in 0 for x and you get 0. So you do know that this graph crosses right there. So we've got a little bit of information. If we want to find out, what's that? Yep. Okay. Good. So now, if I want to say something about increasing, decreasing, and local min and local max, what do I have to find? The derivative. Okay. So let's go through the derivative process. What is the derivative of the top? 4x times the bottom, which is x squared minus 1, minus the top, 2x squared, times the derivative of the bottom, 2x. All over the bottom squared. If we reconcile this, or simplify it, excuse me, we end up with a 4x to the third minus 4x minus 4x to the third over x squared minus 1 quantity squared. What does that simplify to? Negative 4x over x squared minus 1 quantity squared. Well, look at that derivative. Where's that derivative undefined? 1 and negative 1. Do we already have those listed? They'll continue to come up. Where is the numerator equal to 0? 0. You can see that here the numerator is equal to 0. If you set negative 4x equal to 0, you will get 0. So I do have to add that point. I have what happens at 0. What do I have? One of two things. I either have a min or max. Okay? I'm either going to have a min or a max in that situation. Okay? Let's work with our intervals here to decide increasing or decreasing. What number to the left of -1 would you like to plug in? Let's plug in -2. -2 squared minus 1 squared. So that's positive. Plug in -2 to the top. -4 times -2. So I get a positive result. So this is positive. Between -1 and 0, we plug in -1/2. -1/2 squared is a fourth. Minus 1 squared. The bottom's always going to be positive, isn't it? Okay, so let's just focus on top. -4 times -1/2, positive. So this is positive. Yep, we could just plug in the top. Now we try 1/2. -4 times 1/2. Negative. And 2 times -4, negative. So if you wanted to label intervals of increasing, what would you say? -infinity to -1, -1 to 0, decreasing, 0 to, yep, positive 1, excuse me, and 1 to infinity. Very good. We have either a max or a min. Can you identify looking at that? I changed from positive to negative. Is it going to be a max or a min? It's going to be a max. And we know that if you plug in 0, you do get a value of 0. So are we going to have a minimum? Nope, we have no minimum. How do we find concavity and inflection? Second derivative, let's do that. So we had f prime of x was equal to -4x over x squared minus 1 quantity squared. So f double prime of x, I'll use the quotient rule, and I will have derivative of the top, -4 times x squared minus 1 quantity squared, minus -4x, so plus 4x, very good. Chain rule. U squared, x squared minus 1, 2u, 2x. Multiply them, I get 4x times x squared minus 1. So that's the derivative of the bottom. Over the bottom to the 4th power. We need some simplifying. Just think if you didn't have good algebra skills, how difficult this problem would be. So I'm just going to take one small step here so you can see what's going on. -4 times x squared minus 1 squared plus 16x squared times x squared minus 1, all over x squared minus 1 to the 4th. This plus 4x? Because in the quotient rule, when you subtract the second part, you're subtracting then a -4x. Okay, so what can we factor out of the top? I'm just going to factor out an x squared minus 1 because I know that that will cancel with the bottom. So I have an x squared minus 1. And if I factor out an x squared minus 1, what am I left with here? -4 times x squared minus 1. So -4x squared plus 4. Plus 16x squared all over x squared minus 1 to the 4th. What do you do with your x squared minus 1s? Cancel them. You end up with f double prime of x is equal to Negative 4x squared and 16x squared make 12x squared plus 4 over x squared minus 1 to the third. Good boy. That is the second derivative. 12x squared plus 4 over x squared minus 1 to the third. I'm going to put that in the spot where I can find it. That's how I like to organize my work. 12x squared plus 4 over x squared minus 1 to the third. Okay. Where is the denominator undefined? 1 and negative 1 is where we get undefined values. That's where the denominator is equal to 0. Okay, look at this. 12x squared plus 4. Can that ever be equal to 0? Let's think about it. 12x squared, is that always positive or negative? It's always positive, isn't it? How about 4? So when you add these together, you're always going to get a... Yeah, it's never going to be 0. You will never get to a negative number. You'll never get to 0. If you solve for it, you get an imaginary solution. So this is... The top is always positive. It's never equal to 0. So that means we do not have what? We do not have inflection. But we do have concavity. The top is always, 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 always positive. So therefore, we just need to focus on the bottom when we are looking at concavity. Let's plug in what value? Negative 2. My negative 2 squared is minus 1. It's positive overall, so therefore, we put a plus sign. So you're concave up from negative infinity to negative 1. Now what number should I plug in? 0. And if you plug in 0, you get a negative. So therefore, I'm concave down from negative 1 to 1. Now if I plug in 2, I have a positive result. Time to draw the graph. Look at my asymptotes here and everything that's happening. It's positive, so therefore it's concave up, and it is increasing. So does it go on the top or the bottom? It goes on the top. It looks like this. Look at in the middle. It has a, what was this point? Was it a max or a min? It was a max, and it's concave down because of the negative. So what does that look like? It looks like a parabola. It's not exactly a parabola because it follows asymptotes. Parabolas will go on forever in both directions. But this does look like a parabola. Follows the asymptotes. Has that kind of shape. And then the last part is concave up, and it's decreasing. Is that going to go on the top or the bottom? Top. What do you think? Did we do a good job? It's right on. It's perfect. Tomorrow we'll finish off the trig one, and you'll have some time to work. Today I'll give you a couple problems to practice. Okay, so you guys, I've now given you, you had, just to let you know, because I know you've been really busy. I'm afraid you've been falling behind. You've had an assignment on limits that approach infinity and negative infinity. That was from section 4.4. You also had an assignment on Friday from section 4.5 that involved graphing functions and curve sketching. Now you have 3 more. Tomorrow I'll give you one more problem or 2 more problems. That'll be it. But please make sure you're on top of this. Tonight, I know that you don't have to study for any finals because they're over, right? After today, they're over. So work on this tonight.